Okay, so here, let's proceed naman sa chapter 7 about floods. So basically, ito na yung parang isa na sa mga application ng hydrology. Okay, and here, according here, no, to estimate the magnitude of a flood, the following alternative methods are available. Number 1, yung rational method. So ito yung isa sa mga pinakasikat because applicable siya sa catchment area to a small size less than 50 square kilometer. Medyo malaki na rin, no, kahit paano. And marami akong project na ginamitan ko ng rational method. Kasi, pag, let's say, meron kang isang site na tatayuan ng structure, tapos gusto mong malaman kung babahain, kung lulubog ba siya sa baha. So, kung ang catchment area na kasama siya is only less than 50 square kilometer, so okay itong rational method. Okay? Others are empirical, unit hydrograph technique, flood frequency studies. Okay. So let's check yung rational method. Very basic lang naman yung formula niya. CIA. Ito lang yung formula niya. So yan. Diba? Discharge is AV. Diba? Sa fluid mechanics. No? So sa kanya, CIA. No? Meron ka pa ring area. No? So lumalabas itong CI mo, yan yung ano mo, velocity mo. Okay? Itong C, analogous to dun sa yung ano kanina, yung curve number sa yung SCS method, no? Such that pagka mataas ang C mo, ibig sabihin, say theoretically 1, ibig sabihin lahat ng buhos ng ulan mapupunta sa asbaha, no? Lahat ng buhos ng ulan will be transferred to the river, no? Kaya pwede kang bahain. Pero kung ang C mo is mababa, let's say 0.3, ibig sabihin medyo marami ka pang puno, marami pang mag-absorb sa rainfall. So yun lang naman yung basic analogy diyan, no? Yung I is the intensity ng rainfall. Yun lang naman yun, no? Let's say, pupunta ka sa Pag-asa, kunin mo yung millimeters per hour na rainfall. Let's say, si Ondoy, no? That's a 100-year return period na flood. Ano yung intensity ng ulan niya? Yan. Then, compute mo doon sa catchment area kung saan siya umulan. Doon nga, sa Marikina watershed. Then mo, compute mo na yung floods. Okay? So, ito yung formula. So, what are the datas we needed? Time of concentration. Yan, na-encounter nyo na yun kanina, no? Sa sinabi nga natin, dependent siya sa ano. Papapansin nyo yung formula niya, dependent sa length. Di ba, naalala nyo yung length ng river? Kasi, parang yun yung travel time ng ulan from the remote part ng catchment papunta dun sa kung saan mo siya i-measure. Halimbawa, nandito yung structure mo. Gusto mo malaman yung baha dyan. So, yung kukunin mong time of concentration is mula doon sa dulo ng catchment mo, pupunta sa location na to. From here up to here. So, something like that, no? Kasi your catchment could be something like this. Okay? Next is Kirby's equation. Ito yung formula, popular formula to relate the time of concentration daw sa length or slope ng catchment. So, ibig sabihin, mapapansin mo, pag mas mataas yung slope, mas mabilis yung time. Makes sense, no? Kasi, ibig sabihin, kung yung elevation mo dito is, let's say, elevation 100, tapos elevation 0 ka dito. So, in terms of slope, ganyan ka-steep yung slope mo. Whereas kung that is only elevation 50, ito lang yung yung slope mo, mas mabilis yung travel nung ulan dyan kaysa dito. So basically, ganun lang yung idea. Okay, so ito yung formula natin. Next is, yun lang, no? Yun lang yung problem na natin, no? So, an urban catchment has an area of 85 hectares. So the slope of the catchment is 0.006. The maximum length of travel is ano to? 950 ba to? Anyway, nasa book naman yan. Yeah, 950. The maximum depth of rainfall with a 25-year return period is as below. Yan. So, given na yung 25-year return period. And how do you, paano nyo mga makukuha to, yung mga ganyan depth, return period? Doon sa earlier problems natin, no? Irarank mo siya, tapos i-divide mo sa yung rank niya divided by the number of data sets. Okay, so yan po. And then, ang tanong is, if the culvert for a drainage at the outlet of the area is to be designed for a return period of 25 years, yan naman yung typical na return period na ginagamit to design yung culvert, yung drainage natin. Estimate daw the required peak flow rate. Kasi ang culvert natin is bilog, halimbawa. So, pag nakuha mo yung Q na papasok dyan, which is 25-year return period, masisizing mo na to. Yan. Okay, so ibig sabihin, pag hindi mo na-size ng tama yung culvert mo, pwedeng mag-cause ng flood yun. Yan. Estimate the required peak flow rate by assuming the runoff coefficient, yan, given na yung runoff coefficient as 0.3. Diba? So, Q equals CIA. So, given na yung C. Tapos, area ng catchment, given na rin. No? Basically, ito na lang yung problem mo yung I, yung intensity. Okay? So, the time of concentration is obtained by the Kirby formula. So, hindi ko napapakita. Ito lang yon. Then, substitute mo lang. Area, 950. Length of travel pala to, 950. Then, 0.006 is the slope. Okay, so, using that formula, I got 27.4 minutes. Yan. So, ibig sabihin, kukunin natin yung depth, no, at 27.4. So, based sa mga data natin, meron tayong depth na 40 at saka 50 kung ang duration ay 20 and 30. Okay, so mag-interpolate ka ngayon, no? Ibig sabihin, ang time of concentration nung catchment mo doon sa outlet, is 27 minutes. Basically, it will take 27 minutes bago pumunta sa outlet mo yung ulan or yung discharge. And meron tayong mga data ng duration ng ulan saka kung ano yung depth ng ulan. So basically kung may data kayo from Pag-asa, pwede nyo itong makuha. Ayan, so by interpolation I got 47.4 millimeters. So which makes sense kasi nasa pagitan ng 40 and 50. So average intensity will be 47.4 divided by the TC, time of concentration. So 103.8 millimeters per hour. So may intensity ka na. Therefore, wait lang. So therefore, yan, by substituting, yan, C, then I times area, hectare. Parang factor lang to, multiply, conversion factor. So I got 7.35 cubic meter per second. So yan na yung isa-sizing mo sa yung culvert. Yung ano na yan, discharge na yan. So let's say kung i-equate mo yan sa A and V, yan, makukuha mo na yung area ng culvert mo. Tapos yung V is yung capacity nung culvert mo, yung kakayanin niyang velocity ng discharge. Okay? So hindi lang sa culvert, no? Pwede rin maging channel. Yan. So let's say magde-design ka ng channel. Kung alam mo na yung Q mo, alam mo na yung Q na nakuha natin ngayon, yan. So, from hydraulics, from open channel, di ba? Q is equal to area times Manning's formula. 1 over N R 2/3 S 1/2. So, makukumpute mo na yung required channel area mo. Okay? So, from the channel area, madidetermine mo na kung ano yung magiging height nung dike mo. Yan, H. Kasi na-compute mo na yung yung design flood mo. However, this is only a 25-year return period. So, kulang pa yan, no? Kung let's say, expect mo ondoy, 100-year. So, mas mataas pa. Mas malaki pang discharge. So, depende yan sa structure mo. At kung saan mo siya i-design. Pag mga culvert lang, well, typically talaga 25-year return period lang. Pag mga drainage and subdivision. Pero pag mga, halimbawa, dike na, ng mga Pasig River, yan, Marikina River, yan, 100-year dapat yung mga yan. Kasi malaki na yung yung damage sa property pag hindi mo siya dinesign ng at that return period. So next is if the urban daw area of example 1 and then yung land use daw niya ay nagbago, no? So nagkaroon ka na ng roads, nagkaroon ka ng residential area, nagkaroon ng mga industrial area. Yan. So basically, yun, 85 hectares pa rin to in total. Pero in-identify na niya yung mga land use. Okay, so runoff coefficient natin sa mga yan, given na. Yan. So papansin nyo yung runoff coefficient sa road, medyo mataas, 0.7. Kasi nga, paved na yan eh. Hindi na yan nag-absorb masyado ng rainfall. Sa loan, medyo pa yan, mababa kasi kaya pang mag-absorb to eh. Residential area, medyo 0.3 kasi ang residential may mga konkreto na rin. And mga industrial area, paved na rin yung mga yan. Kasi mga pabrika. So the solution for that to average the runoff coefficient is ito. Pinapakuha lang pala yung equivalent runoff coefficient. Ito lang yung formula. Parang kinukuha lang natin yung average. So, 8 times 0.7 plus 0.1 times 17 plus 0.3 times 50, yan, 0.8 times 10, divide dun sa total area na 85 hectares, you get this, 0.36. So, because of averaging, nakuha natin yung ating average C. So yun, siguro, let's say magtitesis kayo, no? Let's say mag-flood study kayo, you will do the same, no? I-identify nyo yung catchment area ng lugar nyo na aaralin nyo. Identify nyo ilan yung roads, ano yung residential area, ano dyan yung mga forest, then lalagyan nyo ng corresponding runoff coefficient. Tapos kukunin nyo din yung equivalent runoff coefficient. Then applyan nyo ngayon ng rational method. Q equals CIA. Okay? So next is a 500 hectare watershed has the land use or cover and a corresponding runoff coefficient as given below. So ganun pa rin. So same. Now the maximum length of travel of water in the watershed is about 3,000 meters or 3 kilometers. And the elevation difference between the highest and the outlet point of the watershed is 25 meters. So basically, pag nababasa nyo yan, yung elevation, tsaka given yung length, makukuha mo na yung slope, di ba? The maximum intensity, duration, frequency relationship of the watershed is given by this formula. Okay, now the question is, estimate the 25-year peak runoff and the 25-year peak runoff daw if the forest has decreased to 50 hectares. Ayan, ibig sabihin, dati 250 hectares yung forest, dito sa case 2, 50 hectares na lang. Ayan. And the cultivated land has encroached upon the pasture and forest lands to have a total coverage of 450 hectares. Okay, so number 1, equivalent runoff coefficient. So, kagaya ng ginawa natin kanina. So, ito yung solution. And applying the formula ng time of concentration, di ko napapakita. Refer na lang kayo sa book. Equation 7.4a. Anyway, may arrow naman dito. Ito siya. 7.4a is here. Yan po. Yan. So, ano pa rin siya? Galing pa rin naman siya sa equation 7.4, which is ating Kirby's equation. No? Inano lang, no? Ni-rearrange lang kasi given na yung slope. Yung slope is from the length and the change in elevation. Okay? Oops. Ayan. So, with that formula, na-compute ko na yung time of concentration. Then, makukumpute ko muna si K. Ayan. Then, plug in dun sa formula ng time of concentration. Ang time of concentration natin ay 58 minutes, 58.5 minutes. So, you can imagine 3 kilometers yung yung given kanina. So, it will take yung 3 kilometers na length of travel ng water will take almost 1 hour. Yan. To travel, no? So, calculation of TC. So, yeah. Calculation ng ating TC 0.975 hours. Ang ating ay 25 years. So, yan yung required, no? 25-year peak. Then, ang intensity natin ay using the formula 71.23 millimeters per hour. So, may area na tayo, may intensity na tayo, meron na rin tayong C, average C, na-compute na natin si Q. So, 64.46 cubic meter per seconds. Okay? So, same procedure lang nung ginawa natin kanina. Now, case 2, sabi nga niya, dumami na yung forest natin naging 50 hectares na lang. Yan. Naging 50 hectares na lang daw. And 450 naman yung what's this? 50 hectares. Then 450 yung pasture and cultivated land. So, magbabago yung C natin. So, ito na yung bagong formula. Bagong calculation ng C. So, yun. So, 0.10 times 50 plus 0.3 times 450. So, ang C na natin ay 0.28. So, check natin yung comparison. Kanina, ang C natin ay 0.181. Dahil kumonti yung forest natin, naging 0.28 na. Yan. Now, compute the time of concentration, intensity natin, yung pa rin, 71.23. Area natin, yun pa rin naman. And yun, nabago lang naman yung C. So, naging Q natin is 99.72 compared sa 64.46 kanina. Yan. So, lumaki, no? Lumaki yung discharge. So, yun yung parang basic idea. No? Nabawasan yung forest mo, so lalaki yung discharge. So, mas babahain ka. Okay, that's it. Yun yung pinaka-gist ng rational method. So, ito yung mga table for reference, no? Yung mga C na gagamitin nyo sa flood study. Next is Gumbel's method. So, dito, ang mga problem dito ay mayroon kang data ng ng example. So, meron kang recorded floods sa isang river. Okay? From a period of, so imagine niyo Marikina River, no? Meron tayo doon, may gauging station ang Pag-asa doon, no? Halimbawa. So, meron kang dito, same problem. Meron kang record ng mga floods na yun, no? Then, i-check mo kung yung behavior ng data mo will follow the Gumbel extreme value distribution. Well, so ginawa na rin namin to sa dati namin project. And this is applicable nga, no? Even sa Philippines. So, estimate the flood discharge with a recurrence interval of 100 years. So, malaondoy, no? 150 years. So, by graphical extrapolation. Well, hindi natin gagawin yan, pero may naman dito. May output naman sa book. Okay, so ito yung data. Then, ito yung naging niya. Okay? So flood discharge. Yan, ito. Where's that? So, ang ginawa is nire-arrange yung table, ito, by decreasing order. No? So, ang pinakamalaki natin is 7826, which is this one. Yan. So, ito siya. Tapos, pinakamababa is 4124. This one. Is ito. Okay, 1951. Oops. No. 1971 ang pinakamababa. Ito, 1971. This one. Tama? 1971. 1,971 cubic meter per second. Then, ang pinakamataas is 7,826. So, nakita na natin yun kanina. So, yan. In-arrange siya. So, ang total number ng datasets natin ay 27. Kasi, from 1977 to 1951. Okay? And then, paano na-compute yung T sub P? Nagawa na natin to actually, no? So, kanina, di ba? M over N plus 1. Yan yung probability. So, yung T, binaliktad lang, no? N plus 1 over M. So, ibig sabihin, yung 7826 may 28 years. Yan. Na value. Okay? Kasi ang rank niya is number 1. So, N plus 1 pala. No? So, 27 plus 1 is 28 over M, which is ang rank niya is 1. Kaya, 28 over 1 is 28. Yan. Okay? And then, next is yan. Then, pwede nyo i-input sa calculator yan. Makukuha mo yung standard deviation. Yan. So, lalabas na standard deviation niyan is 1,432.6 cubic meter per second. Tapos, yung mean is 4,263 cubic meter per second. Tapos, meron table si Gamble from table 7.3 and 7.4. Pag for N27, makukuha mo yung corresponding Y and S. Okay? So, nakuha niya is 0.5332 and 1.104. So, tandaan natin, no? 27 yung N. Okay, tapos, where's that? Zoom out ko, no? Tapos, your Y and S. So, ito yung table ng Y and S. So, given na yan, no? Sa Gamble Extreme Value Distribution. Yan na yung value. Tapos, 27 years yung data natin. So, nandito yan. Yan. So, ang na-compute niya is 0.5, 0.53, tapos 1 point something. Okay? Maano niya, no? By interpolation. Okay? Now, after that, pag nakuha nyo na yon, magagamit na natin yung formula. So, ano bang question? Question is verify, okay. Then, estimate 100 year. Okay. Kasi, mag-estimate tayo ng 100-year flood, pero ang given lang natin na data is good for 28 years. Parang ganun, no? Para tayo nag-extrapolate. 28 years lang yung data natin, pero mag-estimate tayo ng 100-year return period. So, ito yung reality, no? Even si Pag-asa, kailan lang ba na-establish yan, no? Medyo bata pa siya, no? Pero we don't know yet kung ano pa talaga yung in-expect nating flood, no? So in order to to estimate, no, scientifically, ito yung one of the ways using Gamble extreme distribution and yung mamaya yung log Pearson type 3. So statistical method siya, no? And so where's that formula? Yan. So, ito yung mga Gamble's equation. Yan. So, alam natin yung mean value. Tapos, yung standard deviation. Kunin mo yung Y sub T. Yan. Okay, frequency factor as K. Ito yung kinuha natin sa table, yan, Y and S. And then, ito yung formula ng standard deviation, no? Pero kaya nyo din itong makuha sa calculator. So, pag nakuha mo na si Y sub T from this formula, yan, or 0.834 log T over T minus 1. Ito siya. Yan, nakuha niya si K because meron na tayong Y and S. Bar Y and S. So, 1.56. Kasi pag nakuha mo na si K, makukumpute mo na si X sub T. Okay? Yan. So, ito yung Y and S from the Gamble table. Tapos, ito na yung K natin. And using the formula, ito yung formula, you will get 6,499 cubic meter per seconds. Okay, so ibig sabihin, for a 10-year return period, I got 6,499. Wait lang. Okay, so kinuha muna pala natin yung 10-year return period, no? To check yung validity nga ni Gamble, no? So, kaya ang sinubstitute natin dito is ln times ln 10 over 9. No? Kasi nga, we choose t equals 10 years to validate si Gamble. So, 2.25037. Ito is equation 7.22, which is ito. Yan. This one, no? T is 10. Okay? Next is, nung nakompute natin si Y, yan. So, we got Y sub T, 2.25307 minus yung Y bar at saka yung S. So, nakompute ko si K. So, ito yung lalabas na value for 10-year return period for 263 plus 1.56 in K times the standard deviation, 1432.6. So, 6,499. Again, 4263 is the, di ba? Is the, I think, the mean, no? Mean value. Yes, okay? So, check natin, no? Sa 10-year return period, ang na-compute ni Gamble ay 6,499. Tingnan natin dito sa ating data. 10-year return period, 6,499. Yan. As you see, ito yung data natin, discharge natin. So, makes sense because 10-year nasa gitna, no? So, 6,499 na na-compute natin. Okay? So, if we do the same to get the 5-year and 20-year return period, ito mo compute nyo. Now, the problem is get the 100 years and 150 years. Then you will come up with 9,600 and 10,700. Okay, so yan yung purpose ni Gamble, no? You can extrapolate. Okay, so next is given naman ay return period tapos yung mga peak flood niya. So estimate daw natin yung flood magnitude sa river na may return period of 500 years. So ganun pa rin using Gamble. So substitute lang natin mga formula, no? So, ito yung formula for 100 year. Ito naman yung formula for 50 year. So, ginagawa natin yan to compute the K. Yan. Kasi given naman yung X dito, given yung X dyan, Tapos, so, find the relationship. Okay, K is equal to Y over S. Yan. Okay. Then, our constant for the given data series. Yes, constant naman talaga to, no? Then, Y100 minus Y50, 5491. So, you will get the relationship. Standard deviation over S is 5491 over 4.60015 minus 3.90174, 7864. And then, where's that? For T equals 500 years, yan. Y is 6.21361. So, Y500 minus Y100 times standard deviation over S minus discharge sa 500 minus 100. Yan. So, makukuha mong discharge is 59,000 cubic meter per second. So, basically, ano lang tayo. Nag-algebra ka lang. No? Next, the mean annual flood of a river is 600 cubic meter per second. And the standard deviation of the annual flood time series is 150. What is the probability of a flood magnitude 1,000 cubic meter per second occurring in the river within the next 5 years? So use Gamble's method and assume the sample size to be very large. So yan, ito yung mean, 600 cubic meter per second. And standard deviation, 150. And ito yung formula. So nakuha natin si K. So, K is 2.667. And another formula ni K is this, Y minus Y bar over S. Okay, and na-compute natin si itong formula na to from this value. Yan. Where K is Y sub T minus 0.577 over 1.2825. Kapag daw marami kang sample size. No? So, applicable yan pag marami kang sample size. And yun naman ang sinabi sa problem. No? Marami ka daw sample size. Then, given yung K, makumpute natin si Y, 3.9970. Tapos, alam nyo na itong formula na to. Yan, nagamit na natin to kanina. So, makumpute mo si T, which is 55 years. Okay, that means, the probability of occurrence of a flood magnitude 1,000 cubic meter per second is once every 55 years or 0.0182. So kung i-convert mo yan, so the probability at least once in 5 years, so ito yung formula, that will be 11.4%. Okay? Kasi ang ating probability is once every 55, no? Ang tanong kasi is once in 5 years eh. So kailangan natin siya i-convert. And to convert that from that probability to a occurrence in a certain year, ito yung formula. Yan. So therefore, that is 11.4%. Next is log Pearson. So log Pearson type 3 distribution. So parang gamble din. Statistical din kasi siya. Kukunin mo din yung standard deviation. Yan, standard deviation, coefficient of skew. Yan, mean value. Yan, N, yung sample size. Then, kukunin din natin yung C sub S. Yan. Adjusted yon, no? Okay, so, kaya meron din siyang table. No? Parang gamble, meron na rin siyang table. So, problem is, for the annual flood series data, given an example, 7.4, estimate naman daw the flood discharge. So, for 100, 200, and 1,000 years, this time using log Pearson, type 3 distribution. So, ganun din, i-rearrange mo yung table. Okay, ito yung ating mga table. 1951. So, ito yung mga discharges natin. No? So, kumpitin mo yung logarithm. Find the logarithm of this. So, log 2947 is 3.4694. Yan, okay? And then, makumpit natin yung C sub S na ang formula ay ito, galing dito. Yan. Kasi may Z tayo, di ba? Meron tayong Z. So, makukumpit mo yung pag may Z na tayo, which is log X. Yan. So, makukuha mo yung mean ng Z na yan, no? And also, yung standard deviation of the Z, of our sample. So, coefficient of skew, ito yung formula. N natin is yung number ng sample. Z minus Z bar, or yung mean nga, cube over N minus 1, N minus 2. Andito yan eh. Should be... Saan yun? Wala. So, gawan nyo na lang ng table, no? Pero, yun lang naman yung, ano dyan. So, if you got the, yung mga yan, ito yun. So, we have 27 data sets. Tapos 0.003, n minus 1, 26, n minus 2, 25. Yan. And this value, you get coefficient of skewness, 0.043. So, ang nakuha niyang standard deviation is 0.1427. Mean value is 3.6071. Next is the flood discharge for a given T is calculated as below. Values of KZ for given T and CS 0.043 are read from the table 7.6. Ayun. 7.6 is ito. Yan. Ang ating ano ba yung legend ito? Yan. So, ang hinahanap kasi sa problem is 100 year, 200 year, and 1,000. So, ito yon 100 year, 200, 1,000. So, yung last 3 column. Tapos, ang question is 0.043. Yan, yung C sub S natin. Ang C sub S natin is 0.043. So, mag-interpolate tayo. Yan. Kaya, nandito tayo sa yan. Yan, okay? So, 2.358. Yan. Between 2.4 and 2.326. Kasi ito yung C sub S natin, no? Between 0 and 0.1. Ang CS natin is 0.043. So, 2.358 for 100 year. This is 200 year, no? Yan, interpolate ka dyan, you get this. Interpolate ka dito, you get this. Ayan. So, may K ka na. Multiply mo sa standard deviation. Ito yon. Then, using the formula, mean plus K times standard deviation, this one. Then, simply get the antilog. Then, you get this. Ito na yung mga discharges natin. For 100 year, 8,782. 200 year, 9,559. And for 1,000 year, 11,400. Okay. So, next is question is for the annual flood series, that's a previous problem, estimate daw the flood discharge for a return period of 100, 200. So, same pala, no? This time, ang CS daw natin ay 0. Okay. By using log normal. Okay. Sa log normal, ang CS mo ay 0. Yan. So, 0 corresponds to log normal distribution. Kaya, yung data natin na to is ito agad. Yan. Yan. So, ito yung nabago. No? So, since nabago na to, nabago yung ating KZ delta Z. Yan. Then, yan. Nabago na rin yung ating Z sub T. So, antilog, you get this. So, may changes, no? From 8782, naging 8690. From 9559, naging 9434. 11400, 11170. So, lumalabas daw na mas higher value yung log Pearson. However, as the value of CS is small, the difference is not appreciable. So, basically, nasa range naman yung changes. No? Kasi yung coefficient of skewness natin is maliit, 0.0 something. Kumbaga, yung layo niya, no? sa pag-skewed. Skewed means tabingi. No? Yung pagiging tabingi niya sa real data is maliit. Kaya, yung changes is maliit lang din. So, that is the log Pearson and log normal distribution, mga statistical method. So, last is risk and reliability. Basic lang ito mga to, more on ano lang, review lang ng probability, no? So, ito yung mga formula. Yan, nagamit na rin natin ito kanina. Yan. And then, safety factor, ito. So, question is, a bridge has expected life of 25 years and is designed for a flood magnitude of return period 100 years. So, what is the risk of this hydrologic design? If a 10% risk is acceptable, what return period will have to be adopted? So, hindi ko na i-rewrite yung formula, given naman na yan, no? So, ang ating N is 25 years. Ang dinesign siya sa return period na 100 years. So, using this formula, you will get 0.22. So, the risk is 22.2%. Yun lang yun, no? Then, if the 10% risk is acceptable, ano naman yung magiging return period? Yan. Kasi lumalabas at 22% risk, i-design mo siya sa 100 year. Ngayon, ang tanong is, kung bababaan mo yung risk mo, no? 10% risk lang, no? Ano na yung magiging return period? So, using the formula R is 0.10, substitute mo dito, back-calculate mo yung T, lumalabas 0.9, 1 minus 1 over T raised to 25 is equal to 0.9. So, one equation, one unknown, you will get T equals 238 years or roughly 240 years. Okay, so ibig sabihin, para maging 10% acceptable risk, i-design mo sa return period na 240 years yung bridge. So, mas mataas, no? Mas mataas na return period. Kumpara mo kanina, sa 100 years, ang risk mo is 22.2%. Kumaga mas 10%, nilimit na lang natin kasi sa 10%, no? Mas kailangan natin maging maingat, no? So, kung mas maingat ka, therefore, tataasan mo yung return period, no? Ang mas mataas na return period is resulting to a higher flood discharge. Next is analysis of annual flood series of a river yielded a sample mean of 1,000 cubic meter per second and standard deviation of 500 cubic meter per second. Estimate the design flood of a structure on this river to provide 90% assurance that the structure will not fail in the next 50 years. So, use Gamble's method. Yeah, so, same formula ulit. Ang analysis, standard deviation, and then the mean, tapos 90% assurance, or yung ating risk nga, no? 1 minus 1 over T raised to 50, one equation, one unknown. I'm getting 475 years. Okay? Then, you know the T. Tapos, ito yung Gamble's formula, no? Natandaan nyo. No? Then, get the K. Ito, nagamit na rin natin to. Pag maraming sample daw, ito yung formula. So, y sub t is equal to, yan, dahil nakumpute na natin yung year, makukumpute na natin yung y sub t, 6.16226. Then, nakumpute mo na yung y sub t, plug in mo dyan, makukumpute mo yung k, 4.355. Nakuha mo na yung k, mapaplug in mo na yan dito. So, 1,000 plus 1,000 is the mean value plus k, which is 4.355 times the standard deviation of 500 cubic meter per second, 3177 cubic meter per seconds. Okay? So, I think this is the last problem. Annual flood data of the river covering okay, I think okay na to. covering the period 1948 to 1979 yielded the annual flood discharge a mean of 29,600 cubic meter per second and a standard deviation of 14,860. So may proposed na tulay. Near this site, it is decided to have an acceptable risk of 10% in expected life of 50 years. So actually, this is analogous sa NECP natin, no? We are assuming meron tayong 10%, di ba? Probability of exceedance, no? Tapos within 50 years. And yeah, so hindi lang sa bridge ina-apply yan, no? Sa code natin, yan din yung basic structure natin, no? Yan yun din yung ina-apply nating risk, 10% for a life of 50 years. So estimate the flood discharge by Gamble's method for use in the design of this structure. If the actual flood value adopted is 125,000 cubic meter per second, what is the safety factor and safety margin? So yun, using the same formula ulit. Yan. So 10%, no? So compute that, you'll get 0.9978975, one equation, one unknown, for 75 years. Okay, ibig sabihin, meron tayong 10%, tapos ang life expectancy mo is 50 years. You are designing for a return period of 475 years. Ako, ang shortcut formula ko dyan is ito. Yan. So, which is, di ba, 475, i-round up mo yan. That is almost 500 years. So, divide mo sa 0.10, yung 10% nga. No? So, I got 50 years. So, yun din yung ating N. Okay? So, basically, minultiply mo lang sa 10, no? 50 times 10, no? 50 times 10, that is 500. Yeah. Okay? Risk and then life expectancy. Now, ang question is, the flood magnitude is 475 years. Okay. Ang record length natin is 32 years. So, ang Y natin is from the table, no? Alam niyo nang kumuha niyan, 0.53 and S. Tapos, compute natin yung Y sub T. Ma-compute natin yan kasi given, nakuha na natin yung year, di ba? So, 6.16226. Then, ma-compute natin si K, 5.0248. Then, plug in na yan dito sa Gamble's formula. So, 29,600 plus 5.0248 times the standard deviation na 14,860, you got 104,268 or 105,000 cubic meter per second. So, ang ang Q natin, Q500 lumalabas or Q475 is equal to 105,000 cubic meter per second. Ngayon, ang tanong daw is, dinesign mo yung at the magnitude of 125,000. Okay. So, ang in-expect mo lang na discharge is 105. Pero dinesign mo yung bridge sa 125,000. So, ano ngayon yung factor of safety mo? Yun, divide mo lang, no? 125 divided by 105, so 1.19. Then, safety margin, so 125 minus 105,000. So, meron kang safety margin na 20,000 cubic meter per second. Okay? Kumbaga, let's say, merong baha, no? Na napansin mo, no? Meron ka ng na-reach na nung bridge mo yung ito yung bridge mo. 105,000. Ako. So, meron ka na lang remaining na 20,000 cubic meter per second para maging ligtas yung bridge mo. So, something like that. And how do you know na 5,000 cubic meter per second na yung discharge mo? Doon sa natutunan nyo doon sa di ba? Stage discharge relationship. No? Yeah. By correlating yung stage, ma-compute mo na yung discharge. Yeah. Kung may ka dito, gauging station. Okay, so that's it. So basically, yun na yung ating application ng floods. So yung mga Q. Yan. So pag nakuha mo na yung Q, ayun, magagawa nyo ng yung hydrologic analysis na to, no? Then madi-design mo na yung yung creek, yung river, yung dike niya, no? Okay? Kung gaano kalalim. So itong mga methods na to, itong mga procedure na to. Get the discharge, apply the risk, as safety factor, an acceptable risk na gagawin mo. Yeah. Malalaman mo na yung required depth or height ng bridge mo or even yung dike. Okay?